All right, good afternoon. In the short time we have left, I'm going to cover a few more slides on the BJT. So, okay, so we looked at the NPN transistor, PNP transistor, and we looked at the common emitter configuration for both. Okay, so now let's talk about sorry about that. All right, let's talk about how we can determine the operating mode of a transistor based on the biasing, right? So as a recap, three modes of operation, three regions of operation for a transistor, right? And based on those, we can determine whether the transistor is in saturation or cutoff or is in the active region, okay? And so when we say mode of operation, in this case, the mode is basically trying to determine which region it's operating in. Active, saturation, or cutoff. Okay. Now, out of these three, cutoff is the easiest to check. Okay. The reason I say that is because whether it's an NPN or a PNP transistor, the emitter region must be forward bias. Okay. If the emitter base region is not forward bias, then there are no charge carriers that are available. Okay. So the first thing we need to check is the emitter and base voltage. If the emitter base junction is not forward bias, then it's in cutoff. Hence, that's the first check or first step to take. So check the base emitter junction. And there we have two options. Let's do it this way. If it's forward bias, then again, we have two options. It could be in active or it could be in saturation. But if it's reverse bias, then there's only one option, cutoff. Hence, our first step should always be to check whether the base emitter junction is forward bias. Okay. So in this case, if you take a look, now there's no analysis that needs to be done because the voltages are already given to us. Okay, so this is like the first example. All right, VCC is 12. VBB is 4 volts. V1, meaning voltage at the base, is given to us as 2 volts. Emitter is given to us as 1.3 volts. Okay. So VB is 2, VE is 1.3. From there, if you calculate VBE, 0.7 volts. And if VBE is 0.6 or 0.7 volts, that means that that junction is forward bias, right? Forward bias diode. Again, this is an NPN transistor, so the base must be higher than the emitter. So it's plus 0.7. VBE is 0.7. If this was a PNP transistor, it would be minus 0.7. But the number 0.6 to 0.7 is a clue. Okay, 0.6 to 0.7. So this indicates that the base emitter junction is forward bias. So definitely not cut off. It's either active or saturation. Make sense? Any questions? Again, the first check is to see whether the emitter base junction is forward bias. If it's not forward bias, meaning if it's not 0.6 or 0.7 volts, then it's off. If it's off, the only option is cut off. Now, we established that this is forward bias. Because it's forward bias, it could be active or it could be saturation. For active mode, the collector base junction must be reverse bias, right? Saturation is when both junctions are forward bias. Active is when base emitter is forward bias and collector base is reverse bias. So then we check the voltage at the collector, and VC right here is given to us as 4 volts. So NPN transistor, if we determine VBC, VBC must be forward bias, then it would be saturation. If VBC is reverse bias, then it's cut off. Sorry, not cut off. Then it's active. So check VBC. And what do we see? 2 minus 4. Minus 2 volts. Again, NPN transistor. The base is P-type. Collector is N-type. So if you measure voltage at the base with respect to the collector, that voltage must be 0.6, 0.7 volts forward bias. Since the base collector junction is reverse bias, that leaves only is reverse bias. Therefore, BJT is in active mode of operation. That makes sense to everyone? Now let's take a pause. Let me know if you have any questions. Yes. Sorry, what? Oh, the base collector junction is reverse biased. Because it's an NPN transistor, base is P-type, collector is N-type. So if this was forward bias, then the base voltage would be higher than the collector voltage. But VBC is -2, meaning the base is lower than the collector. So that junction is reverse bias, or reverse bias PN junction, meaning that junction is off. And we can refer back to this slide here. Okay. Yeah, and both junctions reverse bias, then it's cut off. Both junctions forward bias, saturation. Hence, the first step should always be to check the base emitter junction. If base emitter junction is it's reverse bias, the transistor is cut off. The only other option is reverse active, which still means the transistor is off. Okay, so we don't need to check anything else. Base emitter junction reverse bias is cut off. Don't check anything else. If it's forward bias, like in this example, then we check the base collector junction. There is one more way to determine whether a transistor is in saturation or not, and that is to check if VCE, the collector to emitter voltage, is less than or equal to 0.2 volts. Because when transistor hits saturation, the current is saturated. So the current is saturated, then VCE, the collector to emitter voltage, is at its minimum, which is around 0.2 volts. If you remember the characteristics right here, saturation is very close to the origin. VCE on the x-axis is very close to 0, so 0.2 volts. So another check for saturation is VCE less than equal to 0.2 volts. So in this example, VC is 4 volts, VE is 1.3, VCE is 0.7 volts, which is not less than 0.2. So the transistor is not in saturation. BJT is not in saturation. 3 minutes left. Any other questions before I move on? Okay. 4 minus 1.3. So just 0.7. So VC is voltage. So if it's a single subscript, it's measured at the node with your reference to ground. So VC would simply mean measuring at collector with my reference at ground. VE means voltage measured at emitter with reference to ground. And if you say two subscript notation, then the positive reference is at the first subscript, so VC, and then E, the second subscript, is the common or the reference point, negative. So if you're measuring in the lab, positive terminal of multimeter would connect to collector C, and negative terminal of multimeter would go to E. You had a question? Oh, was that what you were asking? I need to go back to elementary school. 0.7. Okay, gotcha. Regardless of the math error, the answer was correct. Okay, 158, 159. I did want to large signal models. Okay, I think we are out of time. So, okay, all right. We'll just pick up here again on Wednesday. Sure, yeah.